Greetings and welcome to the introduction to astronomy. In this lecture, we are going to talk about measurements of time and the calendar and how these are related to different things in astronomy. So let's go ahead and get started. And what we want to look at is, remember, we talked about many of the early astronomers. One of their responsibilities was to develop a calendar. And our calendar is based on various astronomical events. So what do we mean there? Well, let's look at the day, the week, the month, and the year, which are how we tend to measure time. So our day is the rotation of the Earth. Why is our week 7 days? Well, there were seven objects known to the ancients that moved among the stars. The month was about the cycle of phases of the moon, and the year was the revolution of Earth around the sun. So all of these then put together give us our different measurements of time that we use today. So how do we measure a day? How long is a day? Well, it actually varies. So there are different measures of a day. We talk about a solar day as compared to a sidereal day. A solar day, which is what we use for everyday measurement, is exactly 24 hours. This is relative to the sun. The sidereal day, on the other hand, relative to Earth's rotation, is 23 hours and 56 minutes long. So while they're close, they are not exactly the same. Why are they different? Well, they're different because Earth is moving in its orbit over the course of a day. So it takes this Earth 23 hours and 56 minutes to rotate. But at that point, the same point on the Earth is not yet pointing toward the sun. It needs to travel about 1 degree more, which is about 4 minutes, in order for it to point back to the sun again. So the solar day is 4 minutes longer than the sidereal day. Since time was based on the solar day, that is what we used. And that's why that's exactly 24 hours. But the true rotation of Earth's period is 23 hours and 56 minutes. And while we'll come to this later, this has absolutely nothing to do with things like leap years that we will look at later on. So what do we mean by solar time? Well, there are actually more types of solar time. We can have apparent solar time and mean solar time. Mean solar time is what we use. That is the mean solar day being exactly 24 hours. The sundial time is what the sun would read and where the sun is in the sky. This is not the same from day to day. So a sundial used here can tell you the rough time, but it won't be exact because the sun isn't always in the same position. That position changes. And that's by given if when you look at the position of the sun over the course of the year is what we call an analemma. So this is the position of the sun, and it can be a few degrees either east or west of the true south point. So south would be where the sun should exactly be. And this is going to be where it varies. And that varies based on the tilt of the Earth's axis and the eccentricity of the orbit. So those two will cause this to spread out. If there was no tilt and the orbit was perfectly circular, and that would be just a point, the sun would always be at the same place. Now, this also relates to how we get time zones. There are 24 regions on the Earth that we use, and those each have a specific time. Now, ideally, these time zones would be exactly north south lines. However, for various political reasons, countries don't want to be divided. Some countries would then be divided and have half their country in one time zone and half in another. So you can see, for example, that most of Europe is in a single time zone. Not all of it. There's a little bit difference to the eastern portions and some of the western portions like Portugal and the Kingdom. But in general, countries try to stay on the same time zone. There are a few exceptions to this. The United States and Canada, being countries that are very spread across, have multiple time zones, as does Russia and Australia. But most smaller countries are set so they will have a single time zone for the entire country. And then we also mention daylight savings time. And all this is a shifting of the time to put sunlit hours in the evening. It really actually has nothing to do with astronomy. So we really won't look at it anymore here. It just is a shifting. It doesn't change anything. It isn't based on anything astronomical. So let's go ahead and look at the calendar now. And we look at the calendar becomes difficult because it is based on astronomical motions that are not related to each other. So for example, the day, month and year, there are 29.5603 days in a month and 365.2422 days in a year, because one is based on the rotation of Earth, one is based on the orbit of the moon around Earth, and the other is based on the orbit of Earth around the sun. There's no reason that these are going to be exact numbers of days. So we end up with months of uneven lengths and leap years because nothing ever fits together quite right. So some of the early calendars, and we looked at Stonehenge previously. Stonehenge had alignments with the rising and setting of the sun and the moon. The Mayans had a complex calendar that was based on Venus, based on the orbit and the observations of Venus. And the Chinese use a 12-year cycle of Jupiter, which gives us the 12-year cycle for the Chinese zodiac. So different calendars based on different motions. So we're not just using those, but other cultures have used other observations and not just the sun and the moon. So our calendars, one of the earlier ones was introduced by Julius Caesar, who gave us the Julian calendar. And in this case, the year was approximated to be 365 and a quarter days. Well, if you remember, it was 365.2422. That's a pretty good approximation. There's a difference of only about 11 minutes. So this is great. Add a leap year every fourth year to keep the calendar from shifting too much over time. And this worked out very well for a while. However, over more than 1,000 years, by 1582, this 11 minutes a year had added up to 10 days. So now spring was starting 10 days earlier, and it would continue. This problem would only continue to grow. So what could be done? Well, we had to redo the calendar, and that was done in 1582. And that is what we use is the Gregorian calendar given by Pope Gregory the 13th. First of all, we had to drop 10 days out of the calendar. So you went to sleep on October 4th and you woke up on October 15th. Why? That just brought everything back into line. All the days that had been added that had become incorrectly over those 1500 years had to then be corrected. So we had to get rid of those 10 days. And also changed how leap years work. So every fourth year is a leap year, just as in the Julian calendar, except century years have to be divisible by 400 to be a leap year. That was not the case in the Julian calendar. So in this case, 1700, 1800 and 1900 were not leap years, but 2000 was. 2100 will not be a leap year. So that keeps everything from changing as much and leads it to a much more accurate approximation. Is it perfect? No, but now it will take tens of thousands or even 100,000 years for it to really start to get too far out of whack. So this is the current calendar that we use, and the adjustment was made just for the century years, that only 3 out of every 4 century years would be a leap year. So let's go ahead and finish up with our summary. And what we've looked at here is the day based on the rotation of the Earth. And there is a difference between the solar day, which is what we use for measurements, and the sidereal day, which is the actual rotation of the Earth, because Earth is moving around the sun at the same time. Our measurements of time are based on unrelated astronomical motions. So we do not get an even number of days in a month or days in a year. And we talked about leap years and how they're used to make adjustments and keep the calendar from shifting over time. So that concludes this lecture on time and the calendar. We'll be back again next time for another topic in astronomy. So until then, have a great day, everyone, and I will see you in class.